and welcome to this Design Practice 2 Module 32. We were talking about different rapid prototyping strategies. The first classification was based on what material you were starting with. So, in context of the solid based materials, we were talking further about the laminated object manufacturing, as popularly known as loam, where I described how laser actually cuts the sheet of plastic or paper, whatever is used as a segment, okay, on a segment by segment basis into different zones. One zone where the actual part segment remains, and the other zone is where the cross hatch portion remains, which can be later on removed as the part needs to be released. Okay. Some example problems are some examples are from these two companies, the loam companies, which actually manufacture parts using the laminated techniques. The original technology was developed by the Helicis Incorporated, which was again acquired by Quorum. There are two major companies which do this technology or use this technology. One is the Cubic Technologies Incorporated, and another is the Kira Corporation Japan. And these are some parts which have been developed by these two different sources. This right here is a valving module for an automotive structure, and this is more like a carry bottle, which has been developed using laminated object manufacturing or loam techniques. The next very important process, which is very widely used across the globe as one of the solid based manufacturing processes, is a FDM or fusion deposition modeling process. So, here the part is constructed by deposition of melted plastics. The step 1 of the process involves a wire of a plastic which is fed into the system. It is about 0.05 inches in diameter, and it is pulled from the spool into a head. Okay. These are different wire spools. There are two different spools from which wire is being fed. One which actually corresponds to the whole part material, the other which is for the support material. They may be same or different polymers. Okay. The program is such that the support material would always be printed in a less dense manner in comparison to the part material, so that the separation becomes easier. And also there is an optimization package which can be worked out in CAD, so that the exact supporting systems which would be needed, or supporting legs which would be needed to create or construct this part in free space, okay, can be to the minimum possible extent, so that the part, when it is recovered, the legs can be taken off, okay, and this way you can have a solid part being pulled off. So, in step 2, the plastic is melted through an extruder. The temperature is taken over the melting point, and then the molding plastic is extruded from an extruder through a pen nozzle, okay, and is dispensed wherever the nozzle moves, and the nozzle would move in a manner so that you have both the nozzles, that is the support as well as the part nozzle, moving through one head, okay, in various parts of the geometry. So, this geometry you have already programmed, and you exactly have filled the volume and space in a CAD package into the portions which are depositing the material and the portions which are depositing the support material. In fact, it will be a very wise idea for you guys to see this process, and if time permits, towards the end of these lectures, I would also give you or make open a video which is how you can do FDM process to build a small millimeter grade part, okay, using various strategies of supports, etc., which will later decouple from the different aspects of the part. So, there are different materials which are used for FDM processes. For example, acrylobutadiene styrene, polycarbonate. Ultim is basically an aerospace grade polymer, otherwise chemically known as polyetheramides. Then there is this polyphenol, sulfonan, PPSF. So, these are some of the materials which can be printed through this fusion deposition modeling process. If I looked at very closely how this part is being shaped, you can see the support material right here in blue and the base material for the part, which otherwise could not have been created in 3D space had the support not existed. Okay, so the support is something that is very less in density, in printing density. It's just like legs for a structure so that it can stabilize while the build up is happening. So this is all a part of the package which comes with the FDM tool through which you can actually design supports in an optimized manner, losing as less parts as possible. So generally the FDM process is quite instrumental in printing these days many complex structures, any geometries. These are a set of single hexagonal resonator sheets. We here by means of the research being carried out in the area of FDM and its applications have developed some materials which can perform, can do acoustic damping of acoustic emissions, acoustic energies to a very high extent, and for that a complex geometry is needed where you have these hexagonal channels as well as small pores and necks interconnecting several such layers of channels. And otherwise, if you were to print or manufacture it using some other method, it would have been really a complex way of manufacturing. But the idea here with the CAD to reality concept as is being promoted by this FDM process, this fusion deposition process, makes it very simple to manufacture such geometries. You can see here small channels interconnecting two different layers, layer 1, L1 and L2, each of which has these honeycomb like structures. So such a kind of a three-dimensional complex shape getting printed through normal process or normal machining is next to impossible, and it can happen only while you are building things additively. So basically the three steps are 3D drawing of both types of structures using SolidWorks software, converting the drawing files into STL formats and printing of the samples using the technique that I have illustrated before. There are many FDM companies. One of the major companies across the world is Stratasys, which has a patented technology for this FDM. Okay, these are some examples. There is a gear assembly being printed using the polymers, okay, used in toy design using different colors. And then there is this monkey sink foil designed by Pro Carlo Sequim UC Berkeley. These are like 5 monkey saddles closed into a single edged toroidal ring, extremely complex geometry, which if not realized may not be so easily able to get visualized mentally, and so therefore in such kind of structures, just before building the structure out, it is probably a wise idea to have some kind of a smaller scale prototype in place, for which 3D printing is 3D printing or rapid prototyping is the way to go. So there are various applications of rapid prototyping. There are applications in design, particularly part design. It can also be applied to engineering analysis and planning sometimes, and then it can do a substantial design intervention in defining or designing or manufacturing tooling as well as other manufactured components. So in investment casting, for example, before you pull out the final die shape, it is always sometimes good to find out what is the negative of the die and whether the part that comes out of the die is actually going to be accurate. Half of the times in prosthetics, when you are building up an artificial leg using a polymer, using injection molding techniques, it is probably a wise idea to do this iteratively to see from a die shape if we can pull out the negative of the cap geometry. Is it really going to be the part which is being intended to get manufactured? Okay, so before putting it in place, before realizing the die, you could actually build up this geometry and see if it is working out before going ahead and CNC machining the die so that it can be put into injection mold. So such are the interventions that RP has, particularly SolidFizz RP has in development of manufacturing processes. So I would like to just take you through some of the aspects of FDM printed samples and some properties. These are just some reference slides, just from an aspect of giving you an idea of how you can mechanically test some of these samples for ultimate yield strength. The samples were printed using a variety of polymers. One of them was of course ABS plus P 430 grade. So generally parts which are printed on a FDM machine can be taken through different tests like compression test as per the ASTM D695 standard, the flexural test where the geometries are being readily available, or the hardness test. This disc here shows the hardness test. The variety of flexural as well as ultimate yield strength testing and hardness testing being carried out through some of these machines here, you can see. And these are, for example, 4 photographs which shows the flexural test happening till the part breaks down. And if we look at the ultimate yield strength, you could do this on a tensioner using this ASTM D638 standard. There are certain standard dimensions for this part. Machine which does which pulls the component and sees the yield point or the fracture point, okay, where failure happens. You could also do the ISOR impact test, which would give you an idea, of the impact resistance of the material being printed. So in several of these tests, we are trying to take through our samples which are 3D printed into different aspects of mechanical characterization. And with the ABS plastic that I said, these are some results that I can share, depending on how they are printed at different rates of pull push forces that the samples are exercised with. This is the original sample. This is the failure at the end of the gauge length of different samples, okay, which are in place. And then we can see the peak stress, the peak load, the yield load, upper yield point of some of these printed in a certain direction, okay. And as the direction of printing may change, it may result in the material properties also vary quite a bit based on what is the direction of printing. So in a way, what can be found out through all these studies and all these tests is that the mechanical strength, mechanical stability of some of the 3-dimensional parts are really highly anisotropic in nature and depends on how the samples are being realized through what direction of printing. Similarly, we have values for flexural test here. Just to give you an idea of how we test some of these samples for mechanical properties or hardness here, you can see about the hardness value to be about 83.167, okay, as per the showed the hardness test based on ASTM D2240 standard. Again, for the particular polymers, there are questions related to their burnability, how they can be, how can they can yield to high temperature or flames. So there are typically flammability tests which are being carried out to address those issues as per the ASTM D635 system, where we can have burning rates of one of the polymers, ABS for example, is 74 millimeter per minute. So these are some baseline values of what would be the mechanical properties or inflammability properties of some of these printed parts, 3D printed parts. So if we compare them with the solid plastic or the solid polymer that is being fed into an FDM system as a wire, they're substantially different, okay, when they go into printed stage. And one of the reasons why that is so is that the printed architecture gives you a sense of strength in a particular direction. So what can designers do with such kind of systems? Designers are able to confirm their design by building a real physical prototype in minimum possible time from CAD to reality. The benefits to improvising the design, converging the design, so there are reduced lead times to produce prototypes, improved abilities to visualize part geometry, early detection of the design errors, increased capability to compute mass properties, okay. I think I showed you some illustration of how mechanical properties are being gauged in comparison to such parts. There are certain problems as well with such rapid prototyping techniques, particularly the FDM process techniques. So, one of them is part accuracy. Obviously, when we talk about zooming close to a part, you will always find a staircase type orientation, and you can see differences between the layers. There is no reflow mechanism between layer 1 and layer 2. For example, if you have printed something in layer 1 and then another in real 2, these are like pyramidal in nature. Okay, so the staircase orientation actually comes up as the FDM process goes up. Had there been a reflow option where they would have slightly leveled off, it would really have changed quite a bit of surface properties, okay, associated with rapid prototyping. And also there are certain shrinkage and distortions of rapid prototype parts. Obviously there is a very limited variety of the input material, and mechanical performance of the parts are limited by the materials themselves. You saw some of the materials, and if we compare that with, for example, metal, there is no comparison. And in engineering parts where we need more of mechanical endurance, sometimes rapid prototyping or FDM processes particularly may not be a very good option. So, load bearing parts are typically, it is preferred that you make it out of metal and not polymer in most of these systems. So, let us now get into the third variety of the RP systems, which are based on powder based or powder beds, and this process is very well known as SLS, or selected laser sintering, where there is granular material present in a bed, and you basically heat treating the material in a manner so that the granules combine to each other through a melting, binding kind of a process, and this way you are building layer by layer architecture for an overall 3-dimensional geometry. So, one of these are selective laser sintering. Then there is another very important process which is also known as 3-dimensional printing. Both of them are powder based processes, and a lot of industry is actually increasingly looking into metal 3D printing, where they take both the SLS and the 3-dimensional printing processes through metallic granules. What is the basic nature of the process? You have a moving laser beam with sinters, heat fusible powders. Powders could be metal powders, or powders even could be polymer powders. Okay, so but they have to be heat fusible, and so you are trying to fuse them in areas which are corresponding to the CAD geometry splice model, and building one layer at a time to build the solid part in a powder bed. So, every time there is a part being constructed, you can think of that the remaining powder which is left over is removed, and a new layer of powder being sprayed, so that that powder can now get freezed, so that the next layer can come up. Okay, so after each layer is completed, a new layer of loose powder is spread across the surface, which is again laser treated or heat fused, so that it becomes a part, one additional layer to the layer that was ending the part below, and this way layer by layer the powders are gradually bonded by laser beam, and they formulate into a solid mass that form a 3D part geometry. The areas in areas not sintered, the powders are loose, they can be poured completely because the laser didn't focus on them, and so you can reuse some of these powders for the spreading process. Okay, in some of the later runs, each layer piston, each layer the piston goes up by a certain amount. Okay, and in the powder feeding piston, and in the second piston, which is the part building piston, the powder which comes out of the powder feeding piston is rolled over the part feeding piston, and this comes down. Okay, so as if the whole part is being built in this manner. So, there are some examples of SLS processes. Initially it was commercialized by Professor Carl Deckard of UT Austin, marketed by DTM Corporation, acquired by 3D Systems again, and these are some plastic parts printed using SLS processes or even metal molds for injection molded parts. Both are examples from the source, DTM Incorporated. They have been currently acquired by 3D Systems in US, Munich, and they form one of the frontline technologies in terms of manufacturing. Let us look at the second aspect of powder based printing, which is also known as the 3-dimensional printing. Here the part is built layer by layer using an inject printer to eject adhesive bonding material onto successful layer of powders. So, here you are not heat curing, but here you are applying some kind of adhesive which joins the powder together. Okay. So, the only difference between SLS and this process is that although both of them have input material as powders, in one case they are heat cured or heat treated, in another case they are bonded together through adhesives. So, or binder. So, the binder is deposited in areas which are corresponding to the cross section of parts as determined by slicing the CAD geometric model into layers, and the binder holds the powder together to form the solid part, while the unbonded powder remains loose to be removed later. So, wherever there is a binder which comes in place, the powders would or the granules of the powder would get bonded to each other firmly. And to further strengthen the part, a sintering step can be applied to bond the individual powders in place. So, this is how it would look like. You have a powder layer deposited, okay, and then there is an inkjet printing head which dispenses the binder material in certain zones, and wherever the binder material is being displaced, they are solidified. So, this part, for example, has been solidified. This is in the process of getting solidified. Here again the binder would be disposed, so this part gets solidified. The remaining is again powder form, can be brushed off or brushed aside, and you can generate this whole bound powder form of part, okay, in place. So, 1 is powder layer deposited, 2 inkjet printing of areas that will become parts, 3 piston is lowered for the next layer, and in this process in 4th layer the powder is taken off and the part is retrieved. Okay. So, that is how 3-dimensional printing is carried out. So, these are some companies with 3D printing options. Z Corporation, for example, you can see an engine manifold for GM racing car, cast after direct shell production casting, or VAS here which has been built through this 3D printing process. Soligen, for example, is another company which works in this area. So, that is how all this rapid prototyping is practiced across the different design and manufacturing industries. So, I would like to end this particular lecture here. In the next module probably we will look up into aspects of rapid tooling, and we will also try to quickly get into the next domain, which is about some linkages, some mechanisms, which is again an essential part of this course, and aspects related to part strengths or structural stiffness or stability. So, as of now I am closing this module. Thank you very much.